Hi and welcome to the third screencast 3.3 from lecture 3. And today we are going to discuss the thermodynamic heat cycles of power stations. The purpose of this screencast is basically to show you how the Carnot engine cycle operates. You should also know how the Rankine cycle and steam cycle work, which is an ideal version of the Carnot engine, which operates more and better with water, for instance. You should also be able to draw the Carnot and Rankine cycles in different property diagrams. You should be able to describe the main parts of the Rankine cycle. You should know some performance measures of power cycles. You should be able to calculate the simplest of the Rankine cycles. And you should know how different properties affect the Rankine cycle and how this affects the components. Okay. Let's first start by introducing the Carnot cycle again, but let's do it with pistons here. And the Carnot cycle is one of the most famous thermodynamic cycles that we have. And it all starts with looking at these pistons, and the first part of it is working here where it's completely insulated. We have this adiabatic compression, which compresses the gas. Once it's compressed, we allow it to come in contact with a hot reservoir at a temperature TH, which makes this thing expand. So we have this isothermal expansion, and then we remove the heat source and setting up the insulating stand again, but the gas will continue to expand and will do so adiabatically. And we then round off with the isothermal compression towards the cold reservoir TC. If we now look at the cycle in a PV diagram, here we have the pressure here on the y-axis and we have the volume here on the x-axis. We have constant lines of constant temperature here. This is the high temperature TH and this is the low temperature TL. And here we start with the compression phase going up to 0.2. From that on we have an isothermal expansion to 3 and then an adiabatic expansion to 0.4. And then we have this again heat removal from 0.4 to 0.1. Another very interesting diagram here is the temperature versus the entropy diagram. And again we have the highest temperature where we have heat addition. We also have the lowest temperature here where we have heat rejection. We start at 0.1, compressing the gas to 0.2. From 0.2 we add some heat isothermally, and from 0.3 we have an expansion process again to 0.4, and from 0.4 we have an isothermal compression back to 0.1 where we reject some of the heat. Now the area contained between point A, 2, 3 and B is all the energy basically in form of heat that we put into the cycle, while the area between A, 1, 4 and B is the area representing the heat that we remove from this cycle. As we can see, we have an isentropic compression and an isentropic efficiency, meaning that the inlet entropy at 0.1 is equal to the outlet entropy at 0.2, and the same here that as S3 is equal to S4. Okay, so to summarize a little bit, we can see here that we have the process diagram for a Carnot process operating as a heat engine. See that it goes clockwise, and for a refrigerator we have the opposite. Okay, this is then called a Carnot refrigerator. Now if we want to put this in a diagram for water, we see here that this is a property diagram for just water, and we have temperature here on the y-axis, and we have the entropy here on the s-axis. And if you remember here, we wanted to have isothermal heat addition and isothermal heat rejection. So basically we are limited to be inside this scope. So this means that for instance, if we have a pressure and volume diagram, again, we have to find a way to put this cycle within these boundaries here. So we go from point 1 to point 2, from point 2 isothermally point 3 to point 4 and back again to point 1. And if we put this in a TS diagram, again we see this, that we have been limited by this saturation bell, or bell-shaped saturation curve basically. In this case cyclopentane. This will change the Carnot process and its limitations basically. You see here we have a much more bend here in the saturation curve, meaning basically that these isothermal lines, if we continue our expansion here, well, we are not going to have an isothermal heat rejection anymore, so we are even more limited here. We can only move in this area. Okay, so the problem basically, by setting up this Carnot engine to work with water, would mean basically that we have this shape, and if we stop the expansion, start the expansion process here along this axis, and expand isentropically down to point 4, we're going to end here at this pressure, meaning that we will have a fairly large amount of moisture in the exhaust gases of this turbine. And a lot of moisture and droplets are associated with corrosion in the turbine because of the droplets that form due to this moisture, and these droplets hit the turbine blades and thus erodes the turbine. So this is not optimum that we have this much moisture in the fluid. Also, we are going to have a difficulty knowing when to actually stop the cooling process and start the compression phase, so we exactly hit point 2 here on this curve. So this will be a little bit difficult, and also we are going to have problems with still having quite a lot of steam that we need to compress together with the saturated liquid here in order to get to point 2. This means that this type of equipment is going to be very difficult to design. We are also quite limited by this bell shape, and frankly the top of this point, the critical point, is the limiting case here. If we remember the Carnot efficiency, stating basically that the efficiency or the thermal efficiency of a Carnot engine is 1 minus the load temperature, or the temperature at the heat rejection, divided by the temperature of the heat addition. Basically saying that, well, then we are limited to have a TH here at this point. So this is not the optimum way of doing it. So what is? Well, looking at the problem of actually aborting this type of cooling process, well, Rankine came to this conclusion here that, okay, but let's cool all the way down to point 1. So point 1 here is exactly on this saturation curve. Well, then we know that we have all the liquid, we have only liquid in this state, which means that we again can compress it to point 2. And it's know that it's only liquid that we are compressing. And from point 2 we again reversibly add heat until we get to point 3, which is on the saturation curve, allowing it to expand down to point 4 and then going back to point 1. Still have a problem with moisture here, but we at least solved this problem. Oh yeah, this type of power plant basically that we have, that could operate in the Rankine cycle is then made up with an ordinary pump that compresses the water isentropically, and it then passes through a boiler, which is basically a big heat exchanger where you add fuel so you can and you combust it to get the QH heat here. Once you have reached the required temperature, 0.3, you let it expand through this turbine and then go back to 0.4 where it's completely expanded, let it again pass through a heat exchanger network and extract the heat from the cycle, condensing it back into a liquid, and the process starts all over again. This pump is called a feed water pump, and the water that is coming from the condenser and going towards the boiler is called feed water. So this is an important term to know. Okay, if we again start looking at this cycle in the form of an enthalpy and entropy diagram, we have on the y-axis here we have enthalpy, and on the x-axis we have entropy. This is very interesting because on this side now we can read the amount of work and heat that we put into the cycle. From point 1 to 2, for instance, we have the pump work, which is a very small part of what we put into the cycle. But here we have the fuel that goes into the boiler, which is a big part. These two combined that we put in must come out in the other part. So on this side we have the turbine work, representing the isentropic expansion from 0.3 to 0.4 and producing the work WT. From 0.4 down to 0.1 we have this heat rejection QL. And just to show again, these lines from 0.1 to 0.4 are constant pressure lines. PA is then lower pressure than PB. In an entropy diagram we can also see that the critical point has moved from the top of the bell down to the a little bit on the side here. Okay, so if we now start to look at the location of the work as we did before, we can now start to look at the equations that describe this. For instance, for the pump work, we have here the mass flow times the enthalpy difference between 1 and 2, which is the pump work then, and the heat addition in the boiler is only the mass flow times the difference in enthalpy between 0.83 and 0.2. The turbine work that we produce is similarly just H3 minus H4 times the mass flow, and the rejection rate of heat here is the mass flow times the difference in the enthalpy here. We now see that we get a thermodynamic efficiency of this cycle as defined before as eta Tejo equals to W net divided by QH, and if we use the equations that we derived here prior to the we see that we get an expressions for the W dot net, which is just W turbine minus W pump, and you get H3 minus H4 minus H2 minus H1, and you divide by the heat that you add during constant pressure in the boiler as H3 minus H2. So here we get thus the expression for the thermal efficiency as a function of the enthalpies in the system. Okay, but this is not the complete truth, because in some sense we have only now looked at the system here. We have looked at an ordinary simple Rankine cycle where we have the boiler, we have a heat addition here in form of QH, we produce a turbine work, we need to add some pump work, and we extract heat here in form of QL basically. I see here also that we have indicated that the net power output from this cycle is the turbine work minus the pump work. Now, as you can see from this picture, we also have this boiler or furnace, and in the boiler or furnace we add air and fuel and combust it in order to get as much energy out of the fuel as we can. This is normally the lower heating value of the fuel. So we add this into the boiler, and the energy we get out we term as Q fuel here. Ideally, we would have all this Q fuel to go into the cycle, but that is not the case, and always have some form of losses that are associated with this combustion process or the heat transfer process. And we use this in then this boiler efficiency, which we here term as eta boiler, or B eta B. And the heat that is lost here is 1 minus this eta B times the fuel that we have. So if we have a 95% efficiency of the boiler, we get 5% of the fuel here, that heat fuel that is lost from the system. So looking at this, we now see that we are going to have a different view of the total efficiency of this power plant. So, as we have discussed before, we have the thermal efficiency, where we basically just look at the network output from the turbine divided by what we term here as the heat input to the cycle. Please remember that this is the cycle and not from the fuel. We term this in terms of enthalpy, and so this equation then basically takes into account everything. But we did also have this boiler efficiency, where we said that the heat that goes into the cycle divided by the fuel, basically the fuel heat, that is what we term the boiler efficiency. We can now then term a total efficiency, which basically says that we want to look at the work that we get out divided by what we could have gotten in if we could extract all the energy from the fuel and have an ideal heat exchanging system to put it into the cycle. And if we expand by QH divided by QH here, we see that we can term the total efficiency as the thermal efficiency times the boiler efficiency here. So let's say we have 40% here and we have 95% here, then 0.4 times 0.95 will give us the total efficiency of the cycle. Okay, a little bit at how this type of performance of this Rankine cycle that we looked on. You see here we have the Rankine cycle, and we want to know how this cycle compares to the Carnot efficiency. So we want to calculate the thermal efficiency, and we want to calculate the Carnot thermal efficiency and find out the answer here. We see here that the Carnot engine would be working between TH and TL here. So the efficiency is 1 minus TL divided by TH. But let's look at the figure here. Okay. Here is also the efficiency of the Carnot engine. We see here that the calculated efficiency is 32.3%, which is a thermal efficiency of the cycle. If we were able to use a Carnot engine, we would instead add 37.1. And just want to give you some of the boundary values here, that in the condenser we have 0.1 bar, and 0.1 bar, you have 1 bar is 100 kilopascal or 0.1 megapascal. And you can see here that the pump work is, I want you to look a little bit at this pump work, how it changes when we add different stuff to the cycle. Seeing that even though we have a fairly large amount of turbine work here, the pump work is not that much actually. The boiler, as we said before, quite a lot of energy that we put into the boiler. We are using a cycle with 30 bars of admission pressure, inlet condition basically, and it's a saturated vapor that we use. Okay, so and please remember to use Kelvin when you do these calculations of the Carnot engine. Okay, Now, this is not the best cycle that we could get. So the interesting question now is, how can we increase this efficiency of the cycle? Well, basically, as Schengel and Bowles points out, that the increase the average temperature at which heat is transferred to the working fluid, or we can decrease the average temperature at which heat is rejected from the working fluid in the condenser. Okay, so this is what we will aim at. Increase average temperature of the working fluid, or decrease the average temperature at heat is rejected, or yeah, so that is what we're going to aim for. Now, the problem with this cycle is you can see here that in comparison to the Carnot engine, we don't have this constant isothermal temperature change here. Instead, we have a temperature that goes from 0.2 all the way up to 0.3. It is reversible, this heat transfer, but still it is not the highest temperature here anymore as it is for the Carnot engine. So, but we can use the definition of entropy in order to get an average temperature instead. Okay, so if we remember that we had the efficiency of the thermal efficiency of the cycle as 1 minus QL divided by QH, we can use this information here to say that, well, we have an isothermal heat rejection. That means we have a constant TL. Well, then the average heat, if it's reversibly done, is temperature times the difference in entropy. The same goes actually for this QH here. However, we need to use a form of average mean temperature here times the S3 minus S1, or actually you could say like this: if we had a differential and you integrate here, you can find this average temperature basically. So using this information, we can now again express the efficiency of the thermal efficiency of the cycle as this, basically just putting in the equations here that we used, recognizing also that S3 equals to S4 and S1 equals to S2, means that we basically get the same expression for the thermal efficiency again, so in terms of temperature. So the same reasoning that we applied on Carnot engine, looking at temperature differences, can now be applied to the Rankine cycle because of this equation basically. Okay, so how do we increase the temperature? Well, basically we could start superheating here. We started in our first example, we stopped here and expanded down, but let's continue to heat, put in heat. We will increase this temperature to 0.3. This will result in that this average temperature will also increase, giving the efficiency the boost that we hope it does. So this is one way of doing it. And looking at this in a PV diagram instead, we see that, well, since this is constant pressure, we are just going to move a little bit out of the wet area here into the more dry area. And we're going to do so by moving it horizontally in this diagram. The benefit of this is actually that once we actually pushed this temperature up to 0.3, the isentropic expansion will end at 0.4, which has also been pushed to the right in this figure, making sure that we will get a little bit drier steam when it enters the condenser, meaning that we will have less problem with the moisture in the turbine. And the further we increase, the more we get into this this line here, the saturation line. And if we continue the superheat, we will now start to expand down to the superheated region. Okay. We also see that when we move the expansion line from this point to this point between 3 and 4, we have a longer expansion line. And this means that more work is produced from this type of turbine. And still, we just maintain the same pump work, meaning that the net work output from the turbine has actually increased. There is, however, a limit to how much we can superheat this turbine, and today that limit seems to be 650 degrees centigrades, and this limit is because of material that we use in the boiler and in the steam turbines. Most plants today use a temperature of 520 to 565 degrees centigrades instead. Cheaper material and fairly good performance can be achieved with this type of inlet conditions. So let's try and do a small calculation of this. You have now 300 bar, but instead of saturated vapor, we have pushed it up to 500 degrees centigrades. We still have 0.1 bar and same boiler and everything else. See here, we have just increased to number 3 here at 30 bar, 500 degrees centigrades. So what will happen now? Well, when we had no superheat, we had 32.3%, but now we have increased these to 35.3%. But however, the Carnot efficiency has dramatically increased to 58.7%. So, but that basically means that I have used this line here as the highest temperature for which the Carnot engine would be able to work, and you see here that that is not the case for the Rankine cycle. And again, although we increased this quite a lot, the turbine work, the pump work is still the same. We do, however, have to push a lot more heat into the system as well. So now we've looked at the temperature that we can just superheat, but actually we can use pressure as well in order to increase the average temperature of heat addition. So looking at this slide here, we see that by just increasing the pressure here in the pump, we can move this saturation temperature a bit up, hoping we will get a larger area in here than we did before and giving more work. The problem now, as you can see, is now we have moved from the superheated position here at point 4 to point 4 dash, and that means that we again increase the moisture of the exhaust in the turbine, and we have seen here that we have moved at the same inlet condition here, so we have the same temperature but at a higher pressure. We can increase the pressure, we can try to do that, but we are still limited here by the critical point. We can't move past that one if we increase the pressure, because even if we do increase above this, we will get this sliding temperature, which we can see in saturation tables of steam. This can be done, but still you won't get the same effect on T average here as you will now that we have large portion of the steam operating in this moist area. Here again you can see here that we have added the supercritical cycle to these type of cycle here. Okay, you do increase the temperature, but you have a more marked effect here on the average temperature compared to here. And the next step that Schengeler told us was basically, well, instead of increasing this temperature, we could try and decrease this one. And doing that, we see here that we have decreased the pressure of the condensing part, making this type of area a lot bigger. Again, by lowering the pressure, we again increase the moisture content, so we have to be aware of the moisture content when doing these type of calculations to see that this is in reasonable values. the expansion line has increased, showing that we will get much more work out of this turbine by prolonging this or elongating this expansion line. When we decrease the pressure to 0.06 bar, and you see here that with the superheat we have 35.6%. If we lower the pressure, we get to 36.3%. And if we take in the same type of turbine with 0.1 bar, but now we add pump efficiency and turbine efficiency, we again get a very low value. So we can see that these irreversibilities influence the performance of this type of cycle quite a lot.